Today, I'll cover a new hydrogen liquefaction plant in Louisiana by Hidrogenii, a joint venture between Plug Power and Olin. I'll also cover an agreement between Oman, the Netherlands, and Germany to establish the world's first liquid hydrogen import corridor. And third, a Forbes article on transforming energy deserts into energy hubs using hydrogen. All of this on today's Hydrogen Podcast. Our first story comes from a Plug Power press release on April 17th of this year. Hidrogenii, a joint venture between Plug Power and Olin, has commissioned a 15-ton per day hydrogen liquefaction plant in St. Gabriel, Louisiana. This facility expands the U.S. hydrogen liquefaction capacity to 40 tons a day, which is a significant step for domestic hydrogen supply chains, particularly for industries like transportation and manufacturing that rely on liquid hydrogen. And so let's break down the technical side. The plant produces 15 tons of liquid hydrogen daily, requiring about 750 megawatt hours of energy per day at 50 kilowatt hours per kilogram for electrolysis and liquefaction, this per industry standards. Liquid hydrogen is stored at negative 253 degrees Celsius with a density of 70 kilograms per cubic meter, meaning 15 tons occupies about 214 cubic meters. Compact enough for efficient transport, but requiring advanced cryogenic systems. The facility likely sources hydrogen from electrolysis, given Plug Power's focus on green hydrogen, using renewable energy to minimize emissions. Compared to hydrocarbon-based hydrogen production, which emits 1.5 million tons of NOx and 500,000 tons of PM2.5 annually in the U.S., that per EPA data, green hydrogen production avoids these pollutants entirely, releasing only water vapor when used in fuel cells. This plant supports applications like fuel cell vehicles and industrial processes. A single ton of liquid hydrogen can power 10 heavy-duty trucks for 500 miles each, meaning 15 tons powers 150 trucks daily, reducing 750 tons of NOx and 150 tons of SOx yearly versus diesel. Geographically, Louisiana's Gulf Coast is ideal. Flat terrain for pipelines, proximity to ports for export, and access to renewables like solar, though water scarcity in the region could challenge electrolysis scaling per global trends. The establishment narrative often highlights such projects as game changers, but challenges still remain. Liquefaction is energy intensive, and the U.S. has only 1,000 hydrogen refueling stations per the DOE data, limiting adoption. Still, this plant is a critical piece of infrastructure showing how hydrogen can decarbonize hard-to-abate sectors while addressing particulate emissions. It sets the stage for broader supply networks like the international corridor we'll discuss next. Our second story comes from Reuters, published on April 16th of this year. Industry groups in Oman, the Netherlands, and Germany have struck an agreement to develop the world's first commercial-scale liquid hydrogen import corridor from Oman to Amsterdam, with the goal of delivering 1 million tons annually by 2030. Partners include Petroleum Development Oman, the Port of Amsterdam, and German firms like Evonik, aiming to supply Europe with low-carbon hydrogen. And the technical setup is fascinating. Oman will produce green hydrogen using its abundant solar resources, or solar capacity in the Middle East can generate electricity at 2 to 3 cents per kilowatt hour, which is ideal for electrolysis. Producing 1 million tons of hydrogen requires 50 million megawatt hours annually, which Oman can achieve with 20 gigawatts of solar capacity operating 2,500 hours a year. This per IRENA estimates. The hydrogen is liquefied at negative 253 degrees Celsius, likely using 10 kilowatt hours per kilogram, adding another 10 million megawatt hours of energy demand. It's then shipped to Amsterdam in cryogenic tankers, with each 10,000 cubic meter tanker carrying 700 tons of liquid hydrogen. That's about 1,400 shipments a year, or 4 per day, to hit that target. Environmentally, this is a win for Europe, where hydrocarbon-based power and industry emit 2 million tons of NOx and 1 million tons of PM2.5 yearly, this per the EPA. Using 1 million tons of green hydrogen in fuel cells or industrial processes could avoid 1 million tons of NOx and 200,000 tons of SOx versus gray hydrogen, which is 10 kilograms of NOx per ton of ammonia equivalent, that per the EPA. However, shipping emissions, likely hydrocarbon-fueled tankers, could offset some benefits unless green ammonia or hydrogen-powered ships are used, which is a growing trend in maritime, this per IMO reports. And geographically, Oman's solar potential contrasts with Europe's limited renewable space, making this corridor a model for global hydrogen trade. But challenges include high liquefaction energy costs and the need for new port infrastructure. Amsterdam's ports must handle cryogenic storage at scale. The narrative of seamless global supply chains overlooks these hurdles, but this agreement shows hydrogen's potential to bridge energy-rich regions with high-demand markets, reducing particulate emissions across continents. And our third story comes from Forbes in an article published on April 15th in the Ford Business Council, Turning Energy Deserts into Energy Hubs. The article argues that regions with limited hydrocarbon resources, energy deserts like deserts in the Middle East, Africa, or Australia, can become energy hubs by leveraging abundant solar and wind to produce green hydrogen, transforming local economies and supporting global decarbonization. Technically, this makes sense. Deserts like the Sahara get 3,000 hours of sunlight annually, producing 4,000 kilowatt hours per square meter per year, this per IRENA. A 1 gigawatt solar plant in such a region costing $800 million generates 3 million megawatt hours per year, which is enough to produce 60,000 tons of hydrogen via electrolysis. That hydrogen can be used locally for industry, like ammonia production, avoiding 600,000 tons of NOx yearly, or exported as liquid hydrogen or ammonia, as we saw with Oman. Wind-rich regions like Patagonia could complement this, with wind turbines at 50% capacity factor producing 4.4 million gigawatt hours per year per gigawatt, or 88,000 tons of hydrogen. Environmentally, this approach is transformative. Producing 60,000 tons of green hydrogen avoids 60,000 tons of NOx and 12,000 tons of SOx compared to gray hydrogen, and 0 PM2.5 versus hydrocarbon-based production. However, water scarcity is a challenge. Electrolysis needs 10 liters per kilogram, so 60,000 tons requires 600 million liters per year. Tough in deserts unless desalination is used, adding 1 to 2 kilowatt hours per kilogram in energy demand, this per energy data. And globally, this strategy leverages geographic disparities. Energy deserts become exporters, while energy-hungry regions like Europe import. Australia's Pilbara region, with vast solar and wind, is already piloting this, targeting 1 million tons per year by 2030, this per web data. The narrative of energy deserts as hubs is promising, but glosses over infrastructure gaps. Pipelines, ports, and refueling stations are sparse, with only 1,000 stations globally, this per the DOE. Still, this vision shows how hydrogen can turn underutilized regions into economic and environmental powerhouses, reducing global particulate emissions. And so let's connect these stories to see how they advance hydrogen's role. The Louisiana plant produces 15 tons per day, or 5,475 tons per year, supporting 150 trucks daily and avoiding 750 tons of NOx yearly. The Oman-Amsterdam corridor scales this up, targeting 1 million tons per year by 2030, potentially cutting 1 million tons of NOx in Europe. Turning energy deserts into hubs, like a 1 gigawatt solar plant producing 60,000 tons a year, avoids 60,000 tons of NOx and supports local economies in regions like the Middle East or Australia. Together, these initiatives could reduce 1.1 million tons of NOx, 220,000 tons of SOx, and 110,000 tons of PM2.5 annually if scaled to 1.1 million tons of hydrogen. And technically, electrolysis, liquefaction, and fuel cells tie these projects together, with storage ranging from cryogenic tanks to ammonia for transport. Geographically, Louisiana's Gulf Coast, Oman's solar-rich deserts, and Australia's Pilbara region show how hydrogen leverages regional strengths. Challenges like water scarcity, energy-intensive liquefaction, and sparse infrastructure persist, but these projects demonstrate hydrogen's potential to build a cleaner energy system, addressing particulate emissions while creating new opportunities. All right, that's it for me, everyone. If you have a second, I would really appreciate it if you could leave a good review on whatever platform it is that you listen to. Apple Podcasts, Spotify, Google, YouTube, whatever it is. That would be a tremendous help to the show. And as always, if you ever have any feedback, you're welcome to email me directly at info@thehydrogenpodcast.com. So until next time, keep your eyes up and honor one another.